Welcome to the Section 9-3 tutorial. This is the part of the reading that's titled Describing Matter. And in this section, they talk about the properties of matter. The word property refers to a characteristic, so matter has certain characteristics that we can use to identify or describe it. And there's two different types of properties you need to worry about. There's the physical properties and the chemical ones. Now, it helps to have a particular type of matter to think about when we talk about the difference between physical and chemical properties. So what I have here is just a chunk of iron. It's an image of iron. And iron is an element. It's on the periodic table of the elements. And this is probably not pure iron, but we're going to pretend that it is. So what are some of the things that we could use to describe it? Well, we could talk about its color. We could talk about the mass or the volume. We could talk about density, which is the combination of those two things, right? We could talk about what it smells like, right? All sorts of things. What else? Well, you could also talk about what temperature it melts at, what its melting point is, or what its boiling point is. Since all substances melt and boil, even iron can melt and boil. We could also talk about what it reacts with chemically. So reactions, Rx, we'll call that. What types of other elements can iron interact with? All of those are ways of describing iron, right? So for the color, you might say it's kind of a dull gray. The mass and the volume would depend on how much you had, but the density of iron is always the same. It's about 7.9 grams per milliliter. So for every milliliter of iron that I have about 7.9 grams. It doesn't have much of a smell, and that's because it doesn't turn to a gas easily. It doesn't melt until you get it up to around 1500 degrees Celsius, which is pretty darned hot, and the boiling point is around 2300 degrees Celsius. But iron also goes through certain chemical reactions. You probably know that iron rusts really easily. You put it in a little bit of water and you expose it to air, and before you know it, it's reacting with oxygen molecules in the air and turning into a reddish substance that looks sort of like this. There's rusted iron, and what happens there is it's actually combining with oxygen in the air and turning into iron oxide, which is what rust is. So which of these different properties are physical and which ones are chemical? That's the question. Well, physical properties are properties that you can observe without changing the substance into something new. Chemical properties go through a chemical reaction in order to see them, so you have to get your substance to change into something else before you know it has that property. So the only property on here that we've discussed so far that's chemical would be the fact that iron rusts. So it's a property of iron that it's capable of rusting in air. In other words, it reacts chemically with oxygen. Everything else about the iron is a physical property. Its color you can observe without causing any changes. How much its mass or volume is, we could measure without changing iron into something new. How dense it is, same thing. What it smells like, same thing. Melting and boiling, we're not going to turn the iron into something new. We're just going to change its state. So anytime a property can be observed without causing a chemical reaction, without causing a new substance to form, you have a physical property. So physical properties are characteristics you can observe without changing the identity of the substance. Examples that I did are going through state changes, melting. That melting point is a physical property. Density is a physical property. Color is a physical property. Those are all examples. Chemical properties, you can only observe them by making your substance go through a chemical change, and when it does that, it's going to become a whole new substance. Like iron turning to rust as it reacts chemically with oxygen, forms a whole new substances with a whole bunch of new properties. And an example of that is reacting with, so reactions. For example, oxygen's the most common one, so if something burns, if it's burnable or combustible, we sometimes use the word combustible. Combustible or flammable is another word, right? Or if it just reacts with something else, then those are chemical properties. And usually they're, except for with oxygen, which have special words that mean that you react with oxygen, combustible or flammable or burnable. aside from that, most of the other chemical properties don't really have names. You just say that, oh, it's a chemical property of iron that it reacts with hydrochloric acid, or that it doesn't react with water. Because the fact that something doesn't react is also kind of a chemical property, if you think about it. Okay, so those are properties of matter. Similarly, you can consider different changes that can happen in matter. And we also break them into physical and chemical. If we expose matter to energy, it will cause it to go through changes. Some of those changes are physical in nature and some are chemical. And this really has to do with the particles and what the particles are doing during the change. So, for example, in a physical change, what you have is a change in particle position, and I'll show you what that looks like. In a physical change, the particles that make up the matter change their position relative to each other, but they don't change who they're bonded to. So let's think about, for example, a molecule of water. So I'll make oxygen, that black atom, and 2 hydrogens on the top. If I were to take water in the liquid state, hold on. There we go, some water in the liquid state. Those are 3 water molecules rotating around each other. A physical change would be something like heating it up so that the particles spread apart and turn to a gas. If they do that, they're going to be the same particles, just further apart. So you'll have the same basic structure for the molecules, but the difference will be how far apart they are and nothing else. So that's a change in position, but not bond partners. Oxygen and hydrogen atoms are still bonded to each other. We haven't changed the water molecule into something new. And this is the second part of what's important about a physical change. In a physical change, no new substances form. Sometimes it can appear like a new substance has formed, like during a state change. If you turn something into a new state of matter, you might think to yourself, I wonder if I've created something new here or not. But you can usually tell that you haven't, because state changes are really easily reversible. You just have to bring the temperature back to where it was originally, and your substance will reform into the form that you had it in before. But changing state is not the same thing as changing into a new substance. So physical changes result in, or any kind of change that you get when the particles change position. It could be a state change, but it could also just be you're chopping something up into smaller pieces. No new substances are created when you do that. Or you could be mixing 2 things together, but they don't have any chemical reaction or attraction to each other, so they just hang out near each other, so they're in different positions than they were before. Those are physical changes. By contrast, a chemical change, the particles don't just change position, they change which atoms are bonded to which. So in a chemical change, particles will change who they're bonded to, and new substances will form. This would be like going back to our water example. If I have water particles, and we'll actually do this later in the year. So I have some water molecules, and I run an electric current through them, and I zap them. And when I do that, you'll see that the result is that we'll actually turn that water into 2 gases, hydrogen gas and oxygen gas. We do it with the water in the liquid phase. So they would start out like this with curved arrows. And then they become all gases afterwards. And we'll trap those gases and do some experiments on them. That is a chemical change. The substances are new. And here's the tricky thing. How do you know when a new substance has formed? Because sometimes it's hard to notice. New substances have new properties, and so what you're going to want to do is, in order to figure out whether a change is physical or chemical, you're going to have to ask this question. Do I have any new properties, and are those new properties conclusive evidence that a real chemical change has happened? Now, the reading, I'm just double checking myself here as I thumb through it, the reading doesn't really go into how to do that. But that is what our lab is going to be about. Our lab is going to be about how to identify whether or not a change that has happened is physical or chemical. It's tricky, it's hard to do, but the first step is knowing the definitions. The last thing that comes up in that reading is something called the conservation of mass, and this is actually a law of nature. This law of nature is very similar to the law of conservation of energy that we learned about, where energy can't be created or destroyed either. All the matter in the universe and all the energy in the universe has always been here, always will be here as far as we can tell. You can move it around, you can make the matter go through all kinds of changes, you can make energy go through all kinds of changes, but you can't get rid of any of it and you can't make new stuff appear out of nowhere. So let's go back to the different changes we were talking about. No matter what I do with that water, if I start out with 3 particles of water, 3 little Mickey Mouse ears, and I make it go through any kind of change, doesn't matter what kind of change it is, physical or chemical, change bond partners, don't change bond partners, doesn't matter. In this case, I'm going to actually make 4 molecules of water because that makes it easier for me to do the math here. So in this case, I'm doing that thing with the electricity where I'm going to make my water come apart into hydrogen and oxygen gas. That's a chemical change, pretty serious change, right? You might say to yourself, hey, the mass is going to change, right? The amount of matter is going to change, Mrs. Stracuzzi. It's going to get lighter, right? I'm turning a liquid into a gas, but no. Mass, the definition I gave you at the beginning of this unit, I gave you 2 different definitions. One was mass is your resistance to changes in motion, but the other one was it's the number of particles that make you up. Look at the number of particles. We had 6 little black circles before, and we've got 6 little black circles after. We had 4 red circles, and we have 4 red circles after. So everybody changed where they were located, who they were bonded to. This is a chemical change, but the mass stayed the same. If you could conduct this experiment in a way where you trapped everything so that nothing could be lost and nothing could be added from the air, you would find that the mass stays the same before and after. And that's it for Chapter 9-3. See you in class.